In 2005, the Samsung SGH-X640 hit the market. It was a standard clamshell mobile phone designed for basic, day-to-day communication. If we examine the specification sheet from a magazine review of the period, we can see the exact optical hardware inside: a fixed 3.35mm focal length lens paired with a 0.3 megapixel VGA CMOS sensor. Contemporary technology reviewers rated this camera poorly. Its output was noisy, it lacked sharpness in low light, and it was deemed suitable only for casual, low-quality snapshots. This device was engineered purely for basic connectivity and affordability. The manufacturer did not design this hardware with scientific or metrological intent. Yet in 2006, researchers at the Budapest University of Technology and Economics acquired this exact handset to test if consumer mobile devices could be repurposed to extract highly accurate geometric data. To measure the phone's accuracy, the researchers first established a baseline truth using a Zeiss Opton 3D coordinate measuring instrument, a device capable of resolving spatial coordinates to the sub-micron level. They utilized a custom-built Manhattan-type test field composed of metal rectangular blocks of varying heights to map specific geometric control points. In later phases of the study, this setup evolved into a secondary test field plate consisting of precision-machined metal cylinders. When the researchers processed the images taken by the X640, the results were highly counterintuitive. The phone mapped the test field with standard deviations under 0.20 millimeters. Extracting a fraction of a millimeter of precision from a compromised VGA lens is achieved through computational redundancy. By analyzing how software forces non-metric hardware into alignment, we can define the exact mathematical boundaries where that compensation collapses. Traditional photogrammetry relies on central projection. In a perfect optical system, an object in the real world, the center of the camera lens, and the point it strikes on the image sensor all sit on a single straight line. This geometry is expressed by the collinearity equations, which map external 3D space directly to internal 2D image coordinates. But apply these to a mobile phone camera, and the math fails. A cheap sensor lacks a stable internal coordinate system. Consumer cameras suffer from severe lens distortion, mechanical instability, and they lack the precise fiducial marks necessary to properly align the image plane. Because the internal optics are physically unreliable, extracting spatial data requires discarding the internal camera coordinate system entirely and finding a direct method of translation. The solution to this optical problem is the direct linear transformation, or DLT, an algorithmic method developed by Abdelaziz and Carrara. This equation bypasses internal calibration entirely. It uses 11 transformation parameters to mathematically bridge an arbitrary pixel grid directly to a physical X, Y, and Z object space. Applying this to the X640 presents an immediate challenge. Identifying an exact measurement point on a low-resolution 0.3 megapixel grid is inherently imprecise. To solve this, processing software analyzes the grayscale values of adjacent pixels. By calculating the gradients between them, the algorithm establishes subpixel coordinates, snapping to intersections with an accuracy of up to 0.3 pixels. DLT shifts the burden of accuracy away from the camera's physical optics. It places the workload entirely onto heavy computational mapping of the image against known control points. To execute this computation, the researchers arranged the camera at multiple standing points, capturing 4 diagonal angles converging on the desktop test field. This chart tacks the X640's error against the number of camera angles. Incorporating 4 overlapping angles sharply drops the error rate. Contrast this with increasing known control points from 7 to 10, which yields diminishing returns. Overlapping angles drive the accuracy. When the researchers repeated this exact experiment using a 2.0 megapixel sensor on a Samsung D600E, the precision improved by only a marginal fraction. In close-range photogrammetry, aggressive network redundancy supersedes raw hardware pixel count. The researchers then designed a second phase of the experiment to test the sensor at a larger object distance of 6 to 8 meters. For this macro-level analysis, they utilized an outdoor ground test field, placing targeted measurement markers across a brick facade. The camera standing points were arrayed in a similar converging pattern to cover the wider scale of the environment. This bar chart compares the desktop results to the outdoor test. The data severely degrades. Spatial errors jump from fractions of a millimeter to roughly 10 centimeters. Simply by moving the camera backward, the average median error increased by a factor of 17. Software algorithms can compensate for internal lens distortion, but they cannot infinitely compensate for the degradation of optical scale. The mathematical law governing this collapse is Fraser's correlation formula. This equation illustrates that the error in an object's calculated coordinates is intrinsically linked to the scale of the image and the object's distance from the lens. If we isolate the variable for distance and the camera constant, their mechanical relationship becomes clear. To maintain accuracy as distance increases, professional photogrammetry solves this problem by physically lengthening the camera lens to increase the camera constant. The Samsung X640 has a fixed 3.35mm focal length. That physical piece of hardware cannot be altered. The unyielding physics of the 3.35mm lens override the DLT algorithm, placing a strict physical cap on the camera's photogrammetric viability at approximately 40 centimeters. Achieving sub-millimeter scientific data using compromised consumer hardware exposes a sharp contrast between an instrument's intent and its latent capability. Rigorous subpixel algorithms and redundant geometric network design provided the necessary computational depth to bridge the hardware gap. While computational models can extract precision from non-metric systems, they remain tethered to the physical constraints of focal length and optical scale.